So, finally, we have reached the last lecture of this course. We have done varieties of derivations from Lorentz transformation, and at the end we were discussing Minkowski diagram, which are geometrical representation of these Lorentz transformations, and you have seen how interesting it is. Last time we derived our time dilation formula from that, linked contraction formula, which is one of the very fascinating equations, can also be very easily derived from this Minkowski's diagram. Let me try to do that. So, last time we considered two events, and these two events in XCT diagram were P1 and P2 such that the slope of this line P1 P2 was more than 1. This angle was more than 45 degrees, and we saw that you cannot find a frame S prime for which this x prime line that you draw here is parallel to P1 P2. This is because for any frame S prime, this line x prime line will make an angle of less than 45 degrees with the x axis. So, whatever frame you choose, it will go like this, x prime corresponding x prime line will go like this, and this has angle more than 45 degrees, this has to be less than 45 degrees. So, in no frame this line can be parallel to this line, and parallel means if you go parallel to this x prime line, x prime changes and t prime does not change. So, there is no frame in which these two will have same time, that we saw. There is a frame in which they occur at the same position, right, because you can have a frame in which the CT prime line is parallel to this P1 P2. That is possible, because this angle has to be equal to this angle and less than 45 degrees. So, this can be parallel to this, and for this particular frame where P1 P2 is parallel to this, t prime can change, x prime will not change. So, these two will have same x prime. So, in that frame these two events occurred at the same place, and the time interval is proper time interval. From there we derive this time dilation thing. So, today what we will do is we will take up two events for which the points P1 P2 are such that the slope of that line is less than 1. So, one event is represented by this P1, another event is represented by this P2, and this line here P1 P2, this line makes an angle with x axis which is less than 45 degrees. So, this angle is less than 45 degrees. Then you can find a frame for which the x prime line is parallel to P1 P2. So, let us draw that line corresponding to that frame, and this is that line x prime, and correspondingly this is the line CT prime, and here for these two events P1 P2 is parallel to x prime, and therefore, if I am going from here to here, x prime is changing, but t prime is not changing. That means, in this particular frame these two events are simultaneous. They are occurring at the same time, but at different positions. So, they are simultaneous events, and there is no frame for which this CT prime can be parallel to P1 P2. So, there is no frame in which these two are occurring at the same position. So, they always occur at different positions, but then in one particular frame the two are simultaneous. Such things are called space like event. Such event, this pair of events is space like in the sense that the space coordinate will always be different. The time coordinate will be same in one of the one particular frame S prime, but in any frame the space coordinate has to be different. They are called space like events. Now you can consider rod, let us say a rod which is, this is x axis and this is y axis. Now this is not Minkowski's diagram, and then you have a rod, a physical rod which is placed parallel to x axis, and you can measure this position at any time t1, this position at any time t2, and x2 minus x1 is the rest length. So, these are two events measuring, these are two events. First event is E1, which is measuring the position of left end, and then E2 is measuring the position of right end. This is x1 at time t1, this is x2 at time t2. Whatever t1, t2, x2 minus x1 is same, that is the rest length. Okay. So, rest length L naught, rest length is this x2 minus x1. Now, let us represent this on Minkowski's diagram. So, here is the diagram, you have x axis, you have CT axis, and the first event is x1 t1. So, let us say first event is p1. So, this is x1 and this is ct1, and then this is x2, this is x1 and this is x2, this is ct1, this is ct2. Now, we go to the frame S prime for which this p1 p2 is parallel to this x prime line. So, go to that frame, and in that frame in which the rod is no more at rest, the length is to be measured. So, the two ends are to be seen or measured, the positions of are to be measured at the same instant simultaneously. So, if this x prime axis is parallel to p1 p2, that is the frame in which these two are measured at the same instant. So, if the rod is moving, but if I am measuring the two positions at the same instant, I am getting the length of the rod in that particular frame. So, if this is the frame in S prime, the time x prime, how do you get x prime and how do you get t prime? For x prime, you have to draw a line which is parallel to this. So, you draw a line which is parallel to this, and this point will be x prime in the scale of this diagram. Remember, actual x prime will be this x prime, and then multiplied by that factor square root 1 minus beta square by 1 plus beta square. So, this is x1 prime here on this line, on this scale, and similarly to get that x prime of this event, again you draw parallel line parallel to this, and that meets my x prime axis here, and this is that x2 prime, and x2 prime minus, so length is equal to x2 prime minus x1 prime, and x2 prime minus x1 prime in this scale is this length, this is x1 prime and this is x2 prime, and this is same as p1 p2, right. This length is same as p1 p2, it is a parallelogram, and so it is p1 p2. But remember, the actual x prime is obtained by measuring this length on this diagram and then multiplied by square root of 1 minus beta square 1 plus beta square. So, that is the length measured in S prime. Okay. The rod was at rest in this S frame, and therefore, no matter what is T1, what is T2, x2 minus x1 gives me the length, and that is the rest length. But in this frame, in S prime, the rod is moving, and we make sure that we measure the two ends at the same instant, and for that this x prime line should be parallel to this, and then I know how much is that length. It is x2 prime minus x1 prime. On this diagram scale it is P1 P2, but for the actual positions it will be multiplied by that. And what is x2 minus x1? x2 minus x1 is simple. In this frame, in S frame, this is x axis, this is CT axis. You draw line parallel to CT axis, it meets here, this is x1 and then this is x2. So, it is just this length and no more scaling factor, and this length is same as this length. Okay. This length here x2 minus x1, this length is same as this length. And what is this length? What is this length? If this is theta, then this length is P1 P2 into cos theta, and since tan theta is V by C, which is beta, cos theta is 1 divided by square root 1 plus beta square, and therefore this quantity is P1 P2 times 1 by square root 1 plus beta square. And now compare this length and this length. This is your rest length L naught, and this is your moving length L prime. So now we compare this L prime is equal to this quantity here, this quantity, which is x2 minus x1, which is L naught. So L naught, I can write L naught here for this thing, P1 P2 multiplied by 1 by square root 1 plus beta square, that is my L naught. So this is L naught, and then what is left? It is only this square root 1 minus beta square. Okay, so you get that expression for length contraction from here. So that is the beauty of this geometrical representation. Just by using parallelograms, parallel lines, a little bit of cos theta, tan theta, geometrical parameters, you can derive all varieties of the derivations from Lorentz transformation. So this is about Minkowski diagram. I can also talk little bit of what is called walled lines. So it is not on Lorentz transformation, but in one particular frame, if you draw this Minkowski diagram, x here, CT here, and then suppose at a certain instant your particle is at the origin. So the event is, what is event? Event is particle is at, say, x equal to 0 and at t equal to 0. Let us say this, at t equal to 0 the particle is origin. So in our real space this is x axis, this is y axis, and the particle is here, and this is the origin of S, and when the particle is here I am calling that instant at t equal to 0. So it is this, and here it is represented by, since x is equal to 0, t equal to 0, it is represented by a point here. Now suppose the particle is at rest, and as time passes it remains at the origin. So here it just remains here, but here the representative point will not just remain here, because time is increasing. From t equal to 0, time is increasing, x does not increase, x remains at 0. So it makes a line as time passes. On this diagram it is a line of this kind, this is. Okay. So as time passes the representative point on the Minkowski diagram will move this way, this way, this way, this way, this way, this way. Such lines are called walled lines. If the particle is at rest here, suppose the particle is at rest here, at this position the particle is just sitting there. So what is the walled line? At t equal to 0, the particle is here. As time passes, time increases. This is the world line. This is the future, in fact. In future, as time increases, it's like this. And t equal to 0 is one particular instant I have chosen. Time was there before that also. So, if you go to that side, the past of this particle, the representative points were somewhere here. So, you can extend this line here and you can put an arrow here. So, this is how the world line is being made. At t equal to 0, it is here. T less than 0, the representative points were here, and then t greater than 0, it's like this. This is the world line. What if this particle is moving at certain velocity v? If the particle moves with certain velocity v at t equal to 0, let us say the particle is here and then it moves in xy in the x direction. Suppose it moves in x direction with velocity v. So, at time t it reaches here vt. Okay, at time t it reaches here. So, x is equal to vt, or t is equal to x by v, or ct is equal to c by v and into x. Ct is equal to c into x and then divided by v. So, it is this, and therefore, on this Minkowski diagram, if you try to draw the world line of this particle which is moving on the x axis with a velocity v, it will be this. Your ct is here. So, y axis, y parameter, this line here, this quantity here is equal to c by v and then x. So, it is a straight line passing through the origin is in this diagram, and the slope is c by v, which must be greater than 1. So, if it moves with uniform velocity, it will have something like this, a world line something like this. The slope has to be greater than 1, this angle has to be greater than 45 degree. Only if v is equal to c, you are talking of a photon. Only if v is equal to c, then the slope will be 45 degrees, this angle will be 45 degree, right. C is equal to v, so it is 1, tan theta is 1. So, if you draw a line, if a photon is there at the origin, this will be the future, this is for the photon. And for any other material particle, it has to be like this. And if the particle is moving in the negative x direction, if the particle is moving in negative x direction, so what will happen? You only have to put a minus sign here. At t equal to 0, it is x equal to 0, and at a later t, it is on this side at vt distance. So, x will be minus vt, and so you will have a minus sign here, and that line will be like this. And if there is a photon moving in negative x direction, this will be the line, photon. Okay, and past of the photon, this is the past of the photon. Photon can come from this side, photon can come from this side. And the particle, for the particle, the past is represented by these. If it is in the positive x direction, it is like this. If it is negative x direction, it is like this. And nothing here, nothing in this region, nothing in this region. So, these kind of representations can be made if you think of a particle which can move in this xy plane. Particle can move in this direction or that direction or that direction, and you try to pick up a Minkowski type diagram. What you will have to do is, you will have to take, let us take ct axis here, and then x here, and then y here, like this, perhaps like this. And then in xy plane it can go anywhere, and this is a time axis. So, as time passes, look for this photon first. The photon can go this way, this way, this way, this way, this way, this way. All these will be at 45 degrees with the ct axis, 45 degree with the ct axis. So, on the surface of this cone, these are the possible lines, these are the possible lines. So, it can be this way 45 degree or 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 this way. So, it is a cone. And similarly, if I extend this cone on the other side, then this will represent me, the photon is coming from here, this is the world line, the photon is coming from here, the photon is coming from here, and so on. And if there is a particle here, wherever it goes, it has to remain in this, and in past it was in this. So, this is, you can call it future cone, and you can call this past cone, and an outside cone is inaccessible to the particle. So, these kind of diagrams are also in use, and with the world line and other things. If two particles collide, what will happen there? The world line of two particles, for them at the collision, the position is same of the two particles, time is same. So, that means the world lines are also colliding with each other or crossing each other or having an intersection. So, these kind of things are done with Minkowski's diagrams. So, that is all I wanted to do in this course. Now, if you revise the thing, if you recall the things how we started, it was started from a very modest observation, and that was the speed of light is same in all inertial frames. The experiments, Michelson-Morley experiments supported this, and then theory, Maxwell's equations, the theory that also tells that speed of light is an absolute constant irrespective of which frame you are doing. If your Gauss law, if your Batch-Savart law, if your Faraday's law, if electricity and magnetism laws, they are working well in a frame, then the speed of light is c equal to square root of 1 by mu naught epsilon naught, which is a fixed constant. It does not have reference to which frame you are talking from. And then the puzzle was that if I am changing the frame and the new frame is moving with respect to the old frame, and I am measuring the velocity of same object in these two frames, how come these two can be equal? So, starting from that small piece of electromagnetic theory and the experiments, this puzzle came up that the velocity transformation from one frame to other frame is not governed by Galilean transformations, and therefore, respecting the principle of relativity, respecting that in this universe you do not have a special frame which you call inertial frame, anything, all inertial frames, if you have one frame which is inertial, then all frames moving with constant velocity with respect to this frame are also inertial, and you cannot pick up one and say this has some special thing, and the Maxwell's equation must be correct in this, the speed of light should be c in this, you cannot. So, respecting that principle of relativity, we changed the Galilean transformation. The Galilean transformation was changed to be compatible with this fact, this piece of information from electromagnetic theory, that speed of light is a fixed universal constant square root of 1 by mu naught epsilon naught, and see how many things came out from that. The Lorentz transformation came out, Galilean transformation was replaced by Lorentz transformation, and then we saw that okay, the Newton's laws were okay with Galilean transformation. Galilean transformations say that if Newton's law are valid in one inertial frame, they are also valid in all other inertial frames. So, the principle of relativity works very well with Newton's law and Galilean transformation. Now, Galilean transformation is replaced by Lorentz transformation, and Newton's laws are not compatible with this new transformation. So, once again the problem, different inertial frames will give you different experimental results which are governed by Newton's laws. And then we realize that no, experiments do show that Newton's laws themselves are faulty at high speeds. If the speed of the particles are high means close to that speed of light in vacuum, close means 10% of that, 5% of that, 20% of that. There are very significant deviations. The experiments show results which are not consistent with the Newton's laws. So, Newton's laws themselves are to be changed. Then we talked of relativistic dynamics, redefined linear momentum, redefined energy, and from that the concept of rest mass energy and total energy came in. So many things are coming out of this, and after all that dynamics and all those things, in this course we went back to electricity and magnetism, because it all originated from electricity and magnetism. And we asked how the electric field and magnetic field transform when we go from one frame to another frame which is moving with respect to the first frame. So, using Lorentz transformations and Maxwell's laws, we could obtain the transformation equations of E field and B field, and we found that electric field and magnetic field are not two separate entities. They are not two separate entities, they are part of one quantity which we called electromagnetic field. Once you fix a frame, yes, this quantity gives you electric field and magnetic field, but you change the frame and it is not the electric field is transforming to electric field there and magnetic field is transforming to magnetic field there, it all getting mixed up. So, you do not have separate physical quantities. It is separate only when you are in a frame, just like a vector. If you decide a frame, then you talk of components, this is x component and that is y component, but the vector is something different. You change the frame and the components will change, but the vector will not change. So, this electromagnetic field is the physical quantity, and electric field and magnetic field are just their parts once you fix up the frame. So, that new concept came in. And then we talked of four vectors, not only that x and t for which the Lorentz transformation was initially derived, set of many more things like energy, momentum, like that. So, they transform according to the same Lorentz transformation, same matrix, and electric field and magnetic field, they transform as second rank tensor. So many things, one after one, one after one, one after another, the sequence kept unfolding and newer things came out, and finally we talked about this Minkowski's diagram where all these algebraic equations can be represented by these geometrical constructions, the axes, parallelograms and rectangles and slopes and straight lines, all that. So, it is a really exciting story, where we start and where we reach, and how many in the journey, how many new adventures we have taken. It is a really very exciting topic and very interesting topic, and I hope I have been able to kept that excitement alive. Okay. So, thank you very much, and all the best. Enjoy physics, enjoy learning, and be very good teachers.